Okay, hello everybody. This is Masoud Ahmasian. I'm chair of ENIGMA-Sleep Consortium and co-group leader of system medicine in INM7 in Jülich Research Center in Germany. It's a great pleasure for me to introduce our speaker today, Dr. Michael Prerau, who is an assistant professor of medicine and also director of neurophysiological signal processing core at the Harvard Medical School. Today, Michael will talk about individualized fingerprints from spindle-like sleep brain waves, provides a powerful new tool for understanding disease. So if you have any question, we can talk later at the end of the presentation, or you can write it in the chat. So thank you, Michael, for accepting my invitation and joining us. The stage is yours. Please go ahead.
Thanks so much.
Thanks.
Get my PowerPoint all queued up here.
I think you can share, yes.
Yep. No, I'm just getting it all set. Actually, one second. Okay, can everyone see okay?
Yeah, perfect.
Okay, great. So thank you so much for having me here today. I'm going to share some work that we've done recently, which we think is really fun and really exciting and can sort of galvanize some aspects of the sleep field that have remained pretty constant throughout the past half century or so. And overall, the point of this talk is to, first of all, understand the history of the way that we have come to understand EEG signals in sleep and what sort of implicit biases come with those, and how we can sort of take the latest and greatest stuff that we have now from a technological sense from other fields and sort of bring it to hopefully revitalize the way we look at something that we have found to be very important. So, throughout the entire world, from as early as you can go back, people have noted the relationship between pollinators such as bees and brightly colored flowers like this primrose here. And for the longest time, just like we're attracted to this beautiful yellow color, we thought that the bees and other pollinators felt the same way. But it wasn't until eons and eons of time that we came to understand the electromagnetic spectrum, that we came to understand that how insect vision worked, and we came to be able to be at a place where we could create technology to look at different wavelengths of the electromagnetic spectrum, that we actually realized that this is what a bee sees if you look in ultraviolet light. And so rather than the color that's attracting them, you have these very clear landing patches here that draw bees in. So it's really important to think that whatever we're looking at through a methodological lens. And really what that's saying is that we have to understand the way in which we look at a system can greatly influence or even bias the way we understand the underlying mechanisms that are creating this system. And so this has been the case in sleep medicine and polysomnography, and we'll sort of talk about that. And so, you know, as everyone knows, perhaps if you're in the sleep field, that when you go in for a sleep test, you go and you get your sleep recorded and other things, and a technician will go and look at a 30-second segment of data throughout the entire night, and we'll score it in a hypnogram below with the different stages. And so we have to ask ourselves, okay, that seems reasonable, but why 30-second epochs? Well, it turns out that in the 1950s and 60s, the Grass Company manufactured the most prevalently used sleep recording device. And they made an engineering decision. They had to say, how big is the table that we're going to have this outfeed of the paper tape upon which the EEG is recorded go out? And based on the size of that and sort of the amount of the feed rate that they wanted to come out, these paper tapes were cut every 30 seconds in order to fill up this table, which they thought was a reasonable number. And so now 60 years later, what are we doing? Well, we are looking at things in 30 seconds, basically because this was an engineering decision. And if you look at the original Retschaffen and Kale's paper, where they described sleep staging to begin with, they said, well, these machines come out in 30-second chunks, and that seems reasonable, so let's codify it. And so we have to ask ourselves, how would sleep medicine be today if they had decided to make their outfeed table twice as long or half as long, or make the outfeed rate twice as fast? So we were looking at 15 or 10 or two-minute segments. And so implicitly, this has added some sort of bias within the way that at least traditional sleep medicine looks at the time course of events, and there are all sorts of practical reasons for that. But at the end of the day, we have to understand that this is really based off of an engineering decision and a practicality decision rather than what is going on in the data. So this is sort of a general standpoint, sort of example here, and we'll see that this sort of follows through. So we asked the question, what if we re-examine sleep data from base principles, sort of using everything that we have from contemporary signal processing? We forget all of sleep medicine, we come at things fresh. And ultimately, we want to move towards things that are objective data-driven rather than things that have been passed down through history and lore. And so what we'll talk about today is sort of re-examining the concept of sleep spindles. What is a sleep spindle? And is that all there is there? And how do we get there? So how did the sleep spindle come to be? Well, if you want to invent the sleep spindle, or you want to find the sleep spindle, you have to go back to 1935. And this man, Alfred Lee Loomis, and he was a real character. He was sort of like an Elon Musk figure of the day. He divested from the stock market right before the stock market crashed in the US in 1929, bought gold, waited for everything to fall down, rebought the stock at pennies on the dollar, and waited for it to come up again, and was extraordinarily wealthy. And he sort of fancied himself this gentleman scientist. And so he built himself a laboratory in Tuxedo Park, New York. And he sent these sort of gold engraved invitations out to all the best scientists of the day. And they would just come, and he said, I'll buy you whatever you want, come to my laboratory and we'll work. And Einstein was there. And I think a bunch of other real luminaries were there, at least for a short period of time. And they did all sorts of interesting things and also some crazy things. They looked at death rays and everything. But out of this laboratory came many interesting and useful things. He was very interested in timing mechanisms, which were things that were critical in the upcoming war for munitions. And also out of here came innovations for radar and also the development of ultrasound. But one of his real loves was trying to understand what's going on in the brain and looking at brain waves through the sort of newly developed, only about 10 years old at the time, electroencephalogram. And so here he is on this drum recorder, which would sort of have a spool going round and round and round, so you could have the entire 8-10 hours of sleep on one system here. And he would do experiments, mostly on his son, Henry Loomis. And he would do some great things like wait till Henry was fast asleep, go in the room and start telling him that he was on a boat that was on fire, and see what he would do. He would wake up screaming, etc. And they say, oh, interesting data. So again, good, interesting scientist, not the best dad. And so out of these recordings, and this may indeed be from Henry himself, but it's hard to say. But he noticed that, and along with Harvey and Hobart, that there were these short little bursts of activity in the electroencephalogram that they see here. And so from those, we really were getting our information by looking at things by eye. There was really no quantitative means at those times for the most part. And so a lot of the way that sleep EEG came about was about, smart clinicians and researchers looking at these miles and miles, literally, of tape wrapped around a tube that they would pull out just like this. And so they published this paper in 1935 where they described this idea of these bursts lasting between 1 to 1.5 seconds at about 14 hertz. And they called them spindles because of how they looked in the record, just sort of the general football shape. And so that's where spindles came from, by people looking by eye at a paper tape. And so, 87, 88 years later, what is a spindle? So a spindle now is really, the real definition of a spindle is anything that an expert identifies as a spindle. There's sort of the circular definition that has sort of worked based off of consensus, And in the US, at least, we have these general guidelines that sort of vaguely describe what a spindle is. And typically they're denoted as occurring between 2.5 to 3 spindles per minute in the literature. And we do know more about what generates them, right? They're linked with thalamocortical networks and generated in the thalamic reticular nucleus and are timed with these hippocampal ripples. We know a lot about them. But again, at least from the EEG, a spindle is what is defined by an expert. But why do we care about spindles? Well, there's a direct relationship between spindle activity and memory consolidation, right? That's taking things from short-term to long-term memory. And also we see that there's major deficits in certain disorders, in particular, autism, schizophrenia, we can see it in Parkinson's, and also with aging. So we see a clear trajectory in some of these spindle properties over time, but also with aging, there's some interesting findings about how those change with age. So they are really important as potential biomarkers for either disease or aging or development. So we're very interested in that. So let's get back to the problem of our methodological lens and bias. Okay, so one of the things that we talked about is that how spindles were discovered by looking by eye at the paper trace, right? And looking at things by eye in the frequency that have specific frequencies that occur during noise and over other activity is very, very difficult. So what I've developed over here, you can see is it's a simulation here where you have sort of three components. You have a spindle component moving around on top, then a colored 1/f noise like you see in EEG component getting bigger and smaller, and then sort of a slow wave and theta component on the bottom. When you sum it together, you get the observed time trace on the bottom. And so what you can see is that sort of depending on how noisy it is and where these spindle-like events occur, they're either easy to see or hard to see, right? Time domain identification is difficult, and you might ask, where are all of the spindles in this? And so what we're sort of asking the question here is that when people looked and defined these traits in terms of their rarity and their properties within the EEG, they're trying to do something very difficult, which is trying to sort of extract these events. And so are we being biased towards only the biggest events that occur in the times of lowest noise? And so what you can see is that it may, maybe you guessed where some of these were, but maybe you didn't see all of them, and it's very hard. And so how does this play out in practicality? Well, this is from the DREAMS database. We had two experts scoring the same spindle records. And you can see in this one, this is the count of spindles that these two experts found. There's a vast discrepancy between expert one and expert two. That expert two scores many more in these two different records, but then you flip it around and expert one scores almost double expert two and this other one. So it's very inconsistent. And so what we end up having is big differences between human scores, between automated algorithms, and between machine learning approaches. And again, these automatic algorithms and machine learning approaches, we can talk more about them, but are based on replicating the gold standard, which is human scoring. So we end up replicating imperfect human scoring rather than trying to see what's actually there. So maybe some of our underlying assumptions are incorrect. We have to see. And so how can we improve on this? So very simply, we're just sort of going to change the way that we look at spindles from base principles, from looking at this in the time domain versus the time frequency domain. And so what we have here is the spectrogram of the same data simulation that you saw before. And in case you're not familiar, spectrogram shows the frequency content across time. So the x-axis is time, the y-axis is frequency, and the depth of color is spectral power at that point. And what you can see is, regardless of how much noise we chuck at we chuck at this signal, you can really see that these spindle-like events are very robustly observed under all conditions. So we said, let's sort of forget about everything that we know in terms of where spindles are and how fast they are and all of these other things, and see if we looked at them from scratch like this, what would we gain? And so what we end up talking about now is the idea of, instead of thinking about what is or is not a spindle, we generalize this. We're talking about transient oscillation. So something that is spindle-like at any frequency, right? And so by definition, transient oscillations in the waveform trace will be time frequency peaks in spectrogram, and we'll be referring to these from now on as TF peak, just to be sure. It's time frequencies peaks, that just these blobs in the spectrogram, which ultimately actually end up being three-dimensional peaks in the spectral topography. But when we look at it, they become these blobs. And so we can sort of investigate this. This is a whole hour of non-REM. And this sigma activity here is where the spindles, fast spindles, typically live. So if we zoom in on this, we see, we see lots of little dots. And we zoom this on and more, we see all of these blobs here, and all of them seem to correspond with something that one might call a spindle in the time domain trace. So now what we do is saying, okay, well, let's sort of go back to base principles and look at this in the time frequency domain. And this is a real trace, and these are the two areas that were scored by an expert as being spindles. And if we look at the spectrogram here, we see that indeed we see these big time frequency peaks, these big TF peaks right above where the scored spindles are. But we also see things potentially equally compelling at other locations as well. Are these the same thing? Are these not the same thing? Are these different? So what did we do? Well, we looked at this, and if you sort of at a first glance, we found that rather than 2 to 3 per minute, when you look at these on average, just in the spectrogram by eye, you found about 10 to 15 per minute. So this is a huge difference that we observed. And so really overall, we saw that pretty much every expert scored spindle corresponded with a time frequency peak, but there were many more time frequency peaks than scored spindles. And that the scored spindles tend to just be at the highest amplitude time frequency peaks at the lowest noise time. So we really sort of thinking about our question is that they just represent, traditional spindles represent a subset of a broader class of transient events. And so we look to prove this, right? And as we said before, what are the issues with existing automated spindle detectors? Well, they're evaluated against human scoring. So the way that traditional automated spindles work is they sort of look at an estimate of power in the frequency range of interest and use a threshold. And so essentially they have a threshold, and when they're above this threshold, then they are for a certain amount of time, then they are a spindle, and if not, they're not. And again, these are based off of these existing assumptions, but the threshold or your training set of expert scored spindles imposes an implicit rarity assumption on the events. And so we believe that these could potentially have a false rarity assumption. So what happens when we lower the thresholds of these? So here's an example of the standard sort of wavelet transform spindle detector that people typically use with and so what you can see here is the bandpass time trace and sort of the spindle frequency range. And here's the amplitude of this signal as a function of from the wavelet transform. And here's our threshold. This is one of the standard thresholds used in the literature. And so all of these purple shading regions here are times that would be scored a spindle. And so you can see that they're denoted here over time, in time with the spectrogram. And then we scored these blobs initially just by hand, but you can see that this is where we scored the blobs. And so what happens if you lower the thresholds of these, you ultimately end up converging to what we see in the actual data. So it's not inconsistent with traditional methods. It's just that the thresholds are set to relate to these lower rates that are observed. And so we did, I'm sort of summarizing this, but we had a paper in 2021 where we did a lot of very, very careful analyses of morphology of what were spindles and what were time frequency peaks and spindles, and what were time frequency peaks and not spindles. But essentially we found that things that were scored by traditional spindle and also as a time frequency peak had this nice clear shape. The ones that were only scored as time frequency peak but not scored by expert had the exact same shape, but were just lower amplitude. And if you look at the amplitude of what the time frequency peaks versus the traditional spindle scores, you see that the spindles are fully nested within this distribution, but there's a clear bias towards high amplitude signals. And a very small percentage were made by time frequency, time domain only, but those had some sort of spindle-like on top of broadband noise. So those were sort of a little unclear to begin with. But for the most part, what we've ended up sort of saying is that we can convince ourselves that the that there's no real distinction between traditional spindles and this broader class of time frequency peak, except for this amplitude value bias. So what does this gain us? Does this gain us anything? Well, what we looked at is night-to-night variability. And so if you look at traditionally scored spindles from a bunch of subjects, the spindle rate of night 1 versus night 2, right? Hopefully you get everything on this y equals x line, but you get it's slightly off, but you get a good correlation, right? Pearson's correlation coefficient of 0.66. So now we look at the ones that we added with just the time frequency peaks from nights 1. And if this is injecting noise, we should do worse. But we actually see that the night-to-night consistency is much, much higher, 0.98. So, and statistically significantly higher. And so we're not just injecting noise into the system, that this is contributing a real level of night-to-night stability that we hadn't seen in the first place. So overviewing this, we say the spindles are defined based off of what's easily to see by eye historically, right? And then automated methods are trying to implement this rarity assumption to agree with the scorers. And we saw that all the TF peaks corresponded with a scored spindle, but there were many TF peaks that were unscored. And then that really spindle morphology and other properties are indistinguishable from TF peaks except for magnitude. So spindles appear to be a subset of this sort of larger level of time frequency peaks in the sigma band. So moving forward, let's go beyond the spindle. Why just look in the spindle range? Maybe these things exist elsewhere. And so what we did now is created a way to look at these time frequency peaks at all frequencies. So and then one of the major problems is we have to make a decision. Is this a peak? Is this not a peak? Is this a spindle? Is not a spindle? That's one of the real issues with detection. And so one of the things we decided to do is say, well, let's forget about defining what is or is not in a specific class. We'll detect time frequency peaks of all places, all shapes and sizes, everywhere. And as long as that they're a statistically significantly observable within our spectral estimator, and we can talk more about that if you have technical questions, if they look like a peak, we'll include them. And instead of trying to look at these properties, we'll look at the distribution of the properties as a function of frequency. So how did we do this? Well, as we said, that these time frequency peaks look like blobs in the spectrogram, but in reality, this is a simulation, but this is real data, are these very clear topographical peaks. And so we created a algorithm based off of this sort of computer vision approach called the watershed technique, which is just a simple way of trying to identify areas that are sort of distinct peaks from each other. And this is sort of based off of the concept that if you have rain falling on a mountain range, you'll have these saddle points where the rain will fall into one basin if they're on this side and another basin if they're on this side. And we sort of flip this upside down in order to get us peaks rather than basins. But this is a pretty reasonable way of looking at things. And we have an approach to fix all to sort of make this work. So we're able to now run this on the actual data from the spectrogram, and instead of the spectrogram, we end up getting tens of thousands across the night of time frequency peaks at all frequencies. And so rather than trying to say these are the peaks we want and these are the peaks we don't want, what we do is we just look at the average rate or density as a function of frequency. And so you can see that we have a really strong high rate here. We use the terms rate and density interchangeably. But a high number per unit time, right where we see the spindle frequency, and then things sort of blip up on. And so when we start looking at subjects, well, what do we see? Well, here we looked at a group of healthy young subjects in their 20s and 30s, and with really good screening for health and sleep problems and all these other things, so nice controls. And so here's what we can see, that if we take this subject and we look at the distribution of the time frequency, the TF peaks, we see this one clear bump in the center, which matches this clear line here. And if we zoom in on the dots, this is where this peak lies, falls right on those dots. But here's another healthy subject. And so you now see two bumps in this, and people have talked about there being fast versus slow spindles, which is what we observe in people mostly as they get older. But we have two bumps here. And we have this, the lines going through this, so you can see how it corresponds to the individual events. Well, here's another healthy subject that is very different, that has a fast spindle peak, but this low alpha activity. which we have found to be very, very prevalent, but underdescribed as occurring in non-REM sleep. But we observe this widely, and it corresponds to these very clear, distinct events here. And then here's another subject that has 3 bumps, again, maybe a fast spindle, low spindle, and this low alpha activity as well. And it's really amazing, but these were all healthy controls, and the sort of highlights the heterogeneity that you see within these, within controls, even within control subjects. And so a lot of, we can attribute some conflicts in the literature to maybe just not properly sub-selecting from this group. But what's also very, very compelling to us is that what I didn't tell you here is we recorded from 2 nights from each subject, and we actually have the recordings of those, the distributions on here. So there's a blue line, but you can also see a thin gray line behind it, and it's pretty much spot on for every subject. That really, we have big differences between the subjects, but night to night it is highly consistent. So to us, that was sort of very, very compelling in talking about individuality of subjects, and also the heterogeneity of subjects. And so now let's get back to understanding about the dynamics of this. How do these things change over time? And so what we can see here is, here are these 2 subjects that we showed before, one with sort of fast spindle peak and the other of a fast and slow spindle peak. And we can say, well, these are highly different subjects, but if you look into it, what's really interesting is that, as we can see here, and it's sort of noted, that you have these lower time frequency peaks, the slower spindles coming on at deeper depths of sleep. So when we collapse across sleep or stage, maybe we're losing something here. And if you look at the deep part of sleep here, where they get into stage 3 sleep, you can actually see some more slow activity that's sort of lost in aggregate. So we want to reclaim, make this, instead of just averaging over the whole night, we want to actually look at how these change dynamically, because maybe these are more similar than we thought. It's just that the sleep dynamics are different here, but the brain states are more similar. And so how can we do this? So you can imagine taking this distribution of TF peaks as a function of rate and frequency for all sleep, and then you can break it up into the different stages that you typically do. And because it's kind of hard to look at lines on top of each other like this, we represent it like a color map. And so what you can see here is that there's sort of diffuse activity in REM, then in non-REM, not REM 1, which is sort of noisy because there's not a lot of data. But then we see a switch in the frequency between stage 2 and stage 3. But are we content with that? No, because in addition to this 30-second assumption, we'll talk about this. In general, in every way thus far studied, sleep is a dynamic and continuous process. And so when we do sort of clinical sleep scoring and staging, we're desperatizing that continuum in state, right? That you can be, at least in some current metrics, wake, REM, or 3 stages of non-REM, right? So we're taking something that's continuous and breaking it up into 5 possible values. So we're desperatizing the state. And then again, like we said, it's 30-second epochs. Now we're desperatizing in time. So we have to ask ourselves, are we content with this loss of temporal and state resolution in describing our data? And so how do we sidestep that, or how do we overcome that? Well, instead of looking at discrete stages, we want to have a continuous measure of depth of sleep. And so to that, we sort of go back to some of the older literature and look at the power of the slow oscillation, or slow wave power. And in this case, we're looking at about 0.5 to 1.5 hertz here. And what you can see is that it is a perfect sort of continuous mirror of the general architecture that you see in the hypnogram. When the slow oscillation power goes up, definitionally slow, you enter slow wave sleep. And so this is great. Again, from the literature, slow wave power is linked with, in the 2-process model, for those who are familiar with it, with the hypnagogic state S, and with sleep pressure. And this is just really easy to compute and ends up being a very robust continuous metric of depth of sleep. So here's what we do now. So what we can do is, here's the spectrogram that we have, and here's the TF peaks for that. And then you can see the slow oscillation power, and I've flipped and mirrored the hypnogram on top of it, so you convince yourself that it does a good job of generally following typical intuition. And then here's what we do. So instead of breaking it up into stages and plotting the heat map of that, we just go and look through slow wave power. So we can take a bin of the lowest slow wave power. We did this in percent slow wave here from the minimum to maximum within the subject. And we have some reasons of that allows us to do it for this particular data set. And we look at what are the TF peaks doing? What's the distribution across frequency of the TF peaks when they're in this bin? And we can plot it here. And then we move up and we move up and we move up. And for each value of the SO power that we have and deeper sleep going from left to right, we then look at the distribution. So this is really like putting on glasses, looking from this depth of sleep going from left to right to now becoming this this visualization that we have here, that we call a slow oscillation power histogram. And so that lets us know, again, frequency and the rate as a function of depth of sleep. And now what we see is a very clear transition from the fast spindles to the slow spindles, where there's a time where it's just the fast spindles, then the fast and slow spindles co-occur, and then just the slow spindles as you're getting deeper and deeper into sleep. So this is a very clear picture. And we can see that the slow power is a nice representation in terms of the actual values that were scored by technicians, that it's transition from REM to N2 to N3 and what we expect. And so again, this is useful because we're looking at all of the TF peaks without making any sort of assumption except some spectral assumptions. And then we're sort of accounting and collapsing out sleep architecture here. And this allows for nice comparisons between subjects and groups without really needing any sleep scoring at all. So now we looked at the sort of depth of sleep change of this, but we want to look at sleep timing. So back to some of these original observations, when people looked at the EEG time domain, they saw that spindles tend to occur sort of at the peak of these K complexes or slow waves here. And so one way that we can quantify this, and people have, is saying, well, we're going to say that the slow wave sort of approximates a sinusoid. And so we can look at where on the sinusoid does the spindle activity occur. And where on the sinusoid we call sort of the phase of the sinusoid. And we think of it like this, that the peak of the slow wave is at 0, and this goes between minus pi and pi. The rising edge is from minus pi to 0, and the falling edge is from 0 to pi. And so this is how we sort of map these things. And so we can compute this as, so if you look at the phase, it has this sort of sawtooth thing where it goes between minus pi and jumps up. And we can see from this, in this paper that many of you may know from Helfrich et al., we can see that there's some interesting changes in phase as a function of age. So younger subjects tend to have their spindles active at the peak of the slow wave, and that sort of shifts down to the rising edge as one ages. So we're able to do this with a time frequency peak. So first we get a spectrum and we compute the slow oscillation. Again, this is just a schematic, not the real slow oscillation, but you'll get the idea. And we look at the times of these peaks and figure out what phase of the slow oscillation these different peaks occur at. And then we mark that. And so now what we can do is we have the hypnogram, the spectrogram, and these time frequency peaks here as dots here. But now what we can do is we can color the dots in our scatter plot as a function of phase. And really without having to do much else, we can see that all of these all of these dots here are sort of a green color, representing sort of a round 0. And this lower band in this sort of low alpha peaks that we discussed before tend to be sort of in this negative pi over 2 area here. And so we can quantify this in the same way that we did the power, and using but using phase now. And so what we can do is we can take a sort of a bin of phase, and that corresponds to this part on the sinusoid, and we can look at the distribution of the activity there and see where it's pointing. So what we're able to do is, in a similar manner, you can see, so this is just showing you too that this lower one tends to be at this average phase here. So what we can do is make something called the slow oscillation phase histogram, where we take, we go through the phase, take a sliding bin of phase, and we slide up and show you what the distribution of TF peaks is as a function of phase in that frequency. So now we have a way of looking at this, and you can see that we kind of have these 2 modes here. we have this big sort of central mode in the general spindle frequency that tends to be above the 0. But in these lower bands, including the low alpha, this tends to be close to minus pi. So this is a great way of looking at sort of the aggregate phase coupling here, that we can see essentially each slice is the the histogram, unrolled, unpolar version of each of these traditional polar histograms here. So let's put this all together. So just as we were shocked at the heterogeneity yet consistency in just looking at the aggregate density over the night, we see that for all the subjects we look at, that there's great heterogeneity between these. And again, these are healthy control subjects, but it's pretty much dead on consistent night after night, even when a subject has a terrible night of sleep for the most part. And so we can think of these as being sort of individualized fingerprint-like signatures for an individual because they are heterogeneous across subjects, yet very consistent night to night. And so we can talk about these and what does this sort of mean, and just to sort of get some terminology that we'll be using in a little bit as we get to some of the applications of this, but we'll call this the sigma high mode, right, corresponding to fast, a sigma low mode corresponding to low spindles, this alpha low activity because it sort of occurs in low alpha, and then this sort of theta activity as well. And so one of the things we can look at is that how in the aggregate does this let us look at disease conditions. And so one of the things we wanted to look at was data from patients with schizophrenia that showed that in general, patients with schizophrenia have a lower density of spindles across the night. And do we see anything else? Do we see anything new? So what we have over here is the average of our healthy controls. And then you can see here's the slow oscillation power histograms across all healthy controls and across all patients with schizophrenia. And you can see some marked differences here. This is just the average difference between those. And so we can sort of quantify each of these modes and see what do we see in terms of differences in the density. And while we observed the previously noted difference in the fast spindle activity, we saw additionally that there were major differences in the alpha low as well as the theta level activity in these patients. So this is a very powerful tool for exploratory analysis to let us understand what is actually going on beyond our little narrow window of just sort of looking at counts of spindles within a very fixed range. So this, in this particular case, lets us suggest maybe 2 new other targets for understanding diagnosis or treatment of the disease, or maybe better understanding the pathophysiology. And so the next thing we can look at too is aging and neurodevelopment. And this is over the Cleveland Family Study, which is available as a part of a public data set. But you can see that there are these sort of major changes that we can observe over age. And we can sort of make this into a video here. But you see that very clearly there are sort of dynamics in both how the SO power structure, how these transient oscillation clouds sort of move over age, and also sort of a shifting backwards of the phase structure, which is what we observe in the literature. So overall, what we've tried to do is go from looking at time domain squiggles to blobs to time frequency peaks to distributions of these peaks over depth of sleep and over phase coupling over these cortical on-off states from the slow oscillation, and really trying to expand the way that we're looking at things. So there's a lot of really great applications for these techniques. And so, what we're able to do is, look at everything from a sort of Gestalt standpoint without making these assumptions, and sort of remove some of the complex dynamics out of the situation, and hopefully allow us to make some connections to better improved mechanistic models, but also from a practical standpoint, look at biomarkers. So, moving forward, we have to understand that we're still looking through a methodological lens in this case, and where can we expand our blind spots and try to look a little further. And so that's sort of where our future work is. But also what we want to do is make sure that these techniques are readily available for everyone to use. So we've created the Dynamo, the Dynamic Oscillation Toolbox, that is open source and available on our website, sleepyeg.org. And we have copious tutorials so that we can allow for everyone to see what they see. So this is available in MATLAB and Python. We have, again, lots of supporting material for this. So anyhow, just to close, I'd really like, there's lots of people I'd like to thank. Mostly the people in my lab, Alex, Viva, Shu Chung, been really great with this. A lot of this work was during the postdoc of Patrick Stokes, listed below, and our collaborators, Dara Manuak and Robert Stickold, instrumental. So I'll stop here and take questions. Thank you very much for your time and for your attention.
Thank you so much for your beautiful talk.